Down at the bottom here I have pressure P2, and up here at the top P1, maybe from the atmosphere. What Pascal is saying is that the pressure all across the bottom of the container is the same. It's pressure P2. And he says that's the same because the depth is the same for all of those points. And now you'll say, well, that's sort of intuitive. I mean, after all, I have this cylinder of liquid that's above this point here, and that cylinder maybe has an area A up here at the top, and it has this volume of fluid that's in it that has a density rho, and it has a height h, so the volume is going to be the area times the height. Mass times g is the weight of the fluid, and so the pressure at the bottom is going to be equal to the pressure at the top plus the weight of that fluid. So you say there's the force. The bottom of the container here has to carry the weight of all that fluid that's above the top. That's very clear, you say. Yeah, maybe. But now how about over here? Pascal says that the pressure is the same at that point. It can't be different or the fluid would begin to flow. But you don't have a column that's height h over that point right there. Or what about over here? And yet the weight of the tall column is way more than the weight over this part over here. Or now how about a container that's shaped like this? Pascal says that the pressure at the bottom of this odd-shaped container is the same as the pressure in this open container that has a fluid that's at the same height. So the pressure at the bottom here is going to be the same as the pressure at the bottom over here. Now that's not so obvious. We live at the bottom of an ocean of air, and when we go up in elevation we expect the air pressure will go down. That's why you feel your ears pop when you go up the mountain. Your eardrums are sensitive pressure gauges, and they tell you when they're unhappy. So you yawn to equalize the pressure on both sides of your eardrums. When you yawn, you open your eustachian tubes to allow air through your throat to the inner side of your eardrums, and you feel this little pop when that happens. Folks who've had ear infections that scarred their eustachian tubes can't pop their ears, and so sometimes they have tubes put into their ears to allow the pressure to equalize. Doctors pierce the eardrum and insert this tiny straw that allows air to pass through to equalize the pressure. So as you go up in height, the air pressure decreases. It doesn't decrease linearly as in an ideal liquid because air is a gas and the gas is compressible. The density of air does change with altitude. But now if I have the Earth down here and I have the top of the atmosphere up here, maybe it's 100 kilometers tall, and I took a square centimeter column cylinder and I weighed all the air that's inside that 1 square centimeter, what I would find is that the amount of air that's in that column, that little straw that's 1 square centimeter in area, is about 1 kilogram. So if I'm at sea level, then what I would see is that there's 10 newtons of air per 1 centimeter squared. And now if you convert that into Pascal, what you get is about 10 to the 5 Pascal. This is what we call atmospheric pressure. It's not unlike the way that liquid, the water, pushed down on us in the deep end of the pool because of its weight. The atmospheric pressure is often called the barometric pressure, and it can be measured with a device that we call a barometer. So let's suppose I hold out my hand, which is roughly 150 square centimeters. There's this huge force of 150 kilograms of air pushing down on my hand. Why doesn't my hand get pushed downward due to all that force? Well, the reason is because there's also 150 kilograms of force also pushing upward on my hand from the bottom. So I don't even feel it. In fact, I'm quite comfortable. I don't even notice that there's this huge force acting on the top of my hand and on the bottom of my hand. So how can I measure this atmospheric pressure if I can't even feel it? I can do it with a tube that's completely filled with a liquid and which is closed at the top end. So let me sketch a diagram of what I mean by this. If I take this black tube and I immerse it in this liquid so I completely fill it, and now let me raise the tube up, then what I'm going to find is that the liquid is going to stay in the tube. As long as I keep the bottom of the tube immersed in the pool, then I'm going to get that liquid to stay there. But if my tube is tall enough, then what I would find is there's going to be some point at which the liquid is going to break free from the top. If I know the height of the liquid that's inside the tube, then I can figure out what the pressure is. Up here, the pressure is equal to 0 because it's empty up here. Down on the surface of the liquid, the pressure is going to be atmospheric pressure. So now I can figure out what the atmospheric pressure is by measuring the height of the liquid in the tube if I know what the density of the liquid is, the density rho. This was done for the first time by Torricelli, after whom is named a unit of pressure that we call the torr, T-O-R-R. He used mercury, which has a density of about 13.6 times 10 to the third cubic kilograms per cubic meter. Torricelli found that the height was about 76 centimeters, 0.76 meters. So now if I put these things in and I take 10 for the acceleration due to gravity, I can find what atmospheric pressure is. What I get is 1.03 times 10 to the 5 Pascal, which comes very close to this 1 kilogram per centimeter squared that I told you about earlier. 1 atmosphere of pressure is defined in this special way when the mercury column is 760 millimeters tall. It's also called 760 torr, and it's also 14.7 pounds per square inch. You're going to see all these units used to represent 1 atmosphere of pressure. And whenever you work these problems, you need to work in a consistent set of units. If I replace the mercury with water, I'd find that the water is 13.6 times less dense than mercury, so the height of the water column would be 13.6 times taller than the mercury column, which is just a hair over 10 meters tall. So you could build a water barometer, and it would have to be 10 meters tall. Do it with mercury, you have a mercury barometer. If the height of the column is more than 760 millimeters, the weather outside, the pressure is high. When you hear the weatherman talk, and the weather's good. If it's less than 760 millimeters, or 29.92 inches if you convert it to inches, then the pressure is low, and the weather is cloudy or stormy. It's good to remember that 10 meters of water is equal to about 1 atmosphere. So that means if you go down in the water by 100 meters, then the hydrostatic pressure increases by 10 atmospheres. Every 10 meters in depth you go down in water is equal to 1 atmosphere of pressure. Let's work a couple of more problems. On a particular day, the atmospheric pressure was 101,000 Pascal. A. What was the pressure at a depth 94 meters below the surface of the sea? B. What was the gauge pressure at this depth? The density of seawater is 1,025 kilograms per meter cubed. Let's start with our equation relating the pressure, the absolute pressure underneath the surface of some water or liquid, and the pressure that's at the top. So the absolute pressure is going to be equal to the gauge pressure, which is rho GH, plus atmospheric pressure. And I know what rho is, I know what G is, and I know what H is. So I'm going to put these numbers in to figure out what the absolute pressure is. I get 1.06 roughly times 10 to the 6 Pascal. Now we're asked in part B to figure out what is the gauge pressure at this depth. Another way you can write our original equation is to say that the absolute pressure is equal to the gauge pressure plus the atmospheric pressure. Let me write it that way. The gauge pressure is this term that we call rho GH. So let's figure out what that is. I end up with 9.64 times 10 to the 5 Pascal. Your textbook has a little different number, and I think the reason is that they're using G is equal to 9.81 instead of G is equal to 10 meters per second squared. This is the gauge pressure. Now you might ask, what's the difference between absolute pressure and gauge pressure and atmospheric pressure? Well, when we talk about gauge pressure, we're talking about if I took an air pressure gauge maybe to measure the air in my tire, see whether my tire is low or not, what it is measuring is the difference between atmospheric pressure and the pressure that's actually inside the tire. So it is measuring what is called the gauge pressure. And this equation here that says that the absolute pressure is the gauge pressure plus atmospheric pressure is a pretty handy one to remember. Let's do another example now. This example makes use of a tube that's called a manometer. The fluid in the U-tube is glycerin, whose density is 1.26 times 10 to the third kilograms per cubic meter. Atmospheric pressure is 1.01 times 10 to the 5 Pascal. A. What is the pressure P in the container? And B. What is the gauge pressure in the container? Alright, now I need to be careful here. What I see is that I have some pressure of the gas that is pushing on the surface of this liquid. And this liquid here has been pushed up on the right side of this tube. So I have atmospheric pressure that's on top, and I have some pressure due to the gas, and the difference is going to be this height here of glycerin that's inside that tube. Now what I claim is that the pressure on the left side must be equal to the pressure that's on the right side, and there is something that's in common with the left side that's also in common with the right side, which is this little amount here. There's going to be pressure due to that, but whatever that pressure is on the left side is going to be balanced by the right side, and so I'm just going to neglect that. And I'm going to say that the pressure of the gas is going to be equal to the atmospheric pressure plus the height of the column, rho times g times h, the pressure due to that. So let's figure out what the gas pressure is, because I know all these other numbers. I find the gas pressure is nearly 1.03 times 10 to the 5 pascals. Well, now what about the gauge pressure? Well, the gauge pressure is going to be the pressure that's due to this little height of glycerin that's in that side. So let's figure that out. Now I'm going to put in the numbers. I get roughly 1764 Pascal, which if you rounded to one significant fig or even two would be nearly 2000 Pascal. So let's review what we've done. In this lesson, we've introduced the idea of gauge pressure, hydrostatic pressure due to the weight of some liquid inside some depth. And we've also talked about enclosed liquids and hydraulic jacks with Pascal's principle. I would now like to end with a short video clip of Walter Leuven in action.
One of the most remarkable things I just mentioned to you is that the period of the oscillations is independent of the mass of the object. That would mean if I join the bulb and I swing downwards the bulb, that you should get that same period. Or should you not? I'm asking you a question before we do this awful experiment. You count. Oh, my expectations are high. I want to hear you loud. You ready for this? Yeah. 3, 2, 1. And here is the femur of an elephant. 0. So I need a volunteer. 1, 2, relax. What does it remind you of? 2, 1, 0. With Walter Leuven, 45.6 plus or minus 0.1 seconds. Physics works, I'm telling you.
Isn't that a great video? Walter Leuven is one of my favorite instructors. Well, for now, that's it.